Hey everybody, Mr. Sharkey back with another exciting chemistry video. Today I wanted to take some time to talk about periodic trends. I know you guys watched a video about it. I know you already took some notes about it, but I think people still had some questions, so I wanted to go over some things pretty quick. The big thing with periodic trends is that everything comes back to Coulombic attraction. So you all should have done an online activity where you looked at Coulombic attraction and saw how some different factors changed Coulombic attraction. So Coulombic attraction is the attraction between charged particles, and there's three main factors that we can look at. The first one, I think, is probably the most familiar to you. If we think about opposite charges, we know that opposite charges will attract each other. So if we're looking at my electron here, my electron is going to be attracted to the positively charged proton. On the second example, if I had two electrons, like I do here in B, then one electron is actually going to repel the other because those similar or those like charges are going to repel. So that's one aspect of Coulombic attraction. It's going to help us explain what's going on with our periodic trends. The other thing we can think about is the distance between charges. So for the rest of these examples, I'm just going to talk about attraction. So we'll always have some positive charge and some negative charge. If we look at this first example, when they're attracted to each other, or when they're pretty close, they're going to be pretty attracted to each other. In my second example, if I increase the distance between the charges, they're still going to be attracted to each other, but they're not going to be as attracted. So as distance increases, this force of attraction goes down. Another key component to help us explain what's happening with our periodic trends. Our third idea is a different magnitude or a different size of charge. So in A, I'm going to draw a larger magnitude. So instead of just one positive charge, let's say that there's three positive charges working on one negative. That's essentially three pulls on that electron. So I like to think about kind of like tug of war. All of a sudden, there's three people pulling on this electron. So this would be a really strong attractive force. But if we draw a second example where there's less charge, so now there's only one proton, and my electron is about the same distance away, because there's only one person, because there's only one proton pulling on that electron, the force is going to be a lot smaller. So to sum up Coulombic attraction, likes are going to repel each other, opposite charges will attract. If there's a bigger distance, there's going to be a smaller attractive force. If there's a less distance, they're going to be more attracted. So I should change my lettering here. This is really picture B and picture A. And then the difference in magnitude. So if there's a larger magnitude, there's going to be more attraction. If there's a smaller magnitude, there's going to be less attraction. Sorry, I'm not going to go back and switch these two pictures around. The bell's about to ring, so I'm going to try to finish this one off. So let's take these ideas and let's apply them to some situations. So here I've picked three different elements from the second period, so the second row of our periodic table. And then I chose ones that were in the same column, but in the third period. So we're just going to look at the second period examples first. So there's three different things that we can think about when we're thinking about our periodic trends. We can talk about atomic radius, which is essentially the size of the atom, so measuring from the center of the nucleus to that outermost shell. We can talk about electronegativity, which is how likely this atom is to bring an extra electron in. So an electron that's just kind of floating around. And then we can also talk about ionization energy, which is the amount of energy it's going to take to rip an electron away. So let's think about distance and the amount of charge. If we look at all three of these examples, lithium, carbon, and fluorine, they all have two energy levels or two shells of electrons. So starting off, the distance from the center of the nucleus to that outermost shell is going to be roughly the same. But the only difference between them is the number of protons in the nucleus and the number of electrons in these shells. So let's look at just one electron in each example. So if I'm focused on this electron for the lithium, and then we'll choose kind of the same one in each other element. In the lithium atom, there are 3 protons pulling this electron in. So imagine 3 people on a tug-of-war team pulling that electron. On carbon, there are 6 protons. So there's 6 people pulling that electron in. On fluorine, there are 9. So if we think about the force of attraction, we could say that lithium has the lowest attraction. Fluorine has the most, and carbon is going to be in the middle. If we think about the repulsive force, there's an electron in the way, right? So that electron is going to push back against the electron we're focused on. But there's 1 electron in each, so we can pretty much say that that's going to be roughly the same. The main difference is the number of protons in that nucleus that are pulling on this electron. So fluorine has the highest attractive force on this purple electron. So that means it's actually going to pull that electron closer to itself. So fluorine will end up having the smallest radius, as all of the electrons in that outermost shell are being pulled by 9 protons. On the other hand, lithium is going to have the largest radius because we've got the same number of energy levels, same number of shells, but there are fewer protons to pull that electron towards itself. And then using the same logic, carbon's going to be in the middle. So let's think about electronegativity. Electronegativity says that we have this lone electron that's going to get pulled in and added to our atom. So how likely is that to happen? We just said that fluorine had the highest attraction on its own electrons. That means that fluorine's also going to have the highest attraction on any random electron that's floating around. So our green electron here is going to be really attracted to that fluorine nucleus. The lithium electron, this green one floating around, is going to have some attractive force, but it's not going to be as much because there's only 3 protons pulling it in. If we think about exactly where this fluorine would slot itself in, it'd probably go over here where there's less electrons, but that's a conversation for another time. Let's just think about electronegativity. So once again, fluorine has the most attractive force, so it's going to pull in that electron the most, so it will have the highest electronegativity. It's got the most force pulling in extra electrons. Lithium has the fewest number of protons, so it's going to have the lowest electronegativity, and then once again, carbon will be in the middle. We'll switch to another color for ionization energy. Ionization energy is the amount of energy that it's going to take to pull an electron away. So we'll look at this same electron that we've been talking about. We said that lithium has the lowest attraction. So if this electron is barely attracted to that nucleus, it's going to be pretty easy for us to rip that electron away. So we're going to end up having a low ionization energy for lithium. If we look at fluorine, fluorine has a higher attractive force, so it's going to have a higher ionization energy. It's going to take more energy for us to rip that electron away. Once again, carbon is left in the middle. So as we go from left to right across the periodic table, atoms that are on the left are going to end up having small radiuses, which means atoms that are on the left are going to have large radiuses, which means they'll have a low electronegativity and a low ionization energy. Atoms on the right are going to be smaller, so they have a higher electronegativity and a higher ionization energy. The difference is when we're going to start looking from top to bottom. So as we go down a row, let's spend some time here to look at the differences between fluorine and chlorine. Right off the bat, what do you notice about the atomic radius of chlorine? Hopefully you see that we have a whole extra shell, so we can say that chlorine is going to be significantly larger than fluorine. And then if we look at an electron again, if we look at a random floating electron, it's still going to be attracted towards that chlorine nucleus, but now there's this whole level of electrons that are repelling, that are pushing back against our new electron. So our electronegativity here is going to end up being less than fluorine, because now there's more electrons in the way of the nucleus. So even though there's more protons, there's a whole nother shell that's kind of protecting that nucleus. This is something that we call shielding. So you might hear that term come up. So chlorine has a little bit less electronegativity than fluorine. The last topic that we can talk about is ionization energy. This electron all the way out here. Chlorine has more protons, but this electron is further away from the nucleus, and there's more electrons pushing against it, just like we saw with electronegativity. So chlorine is larger. It has a lower electronegativity, and it's going to take less energy to rip an electron away. So as you guys have heard, the bell has already gone off, so I'm going to go ahead and wrap this video up. But these trends are going to be similar across these other two examples. So what I'd like you to do to check and see if you have things going, compare carbon and silicone, compare lithium and sodium, and see if you can figure out what would happen to the atomic radius, electronegativity, and ionization energy in each one. Think about the trend as we move from, sorry, for you guys, I guess it's left to right, and then think about what happens as we move from top to bottom. So I'm going to end it here. Sorry that this is a bit of a quick cutoff, but I ran out of time here at the end of the period. Hopefully this video helped out a little bit, and next class, we'll spend a little bit more time talking about periodic trends. Keep in mind, everything's going to come back to Coulombic attraction. So when we ask you to explain or justify, you should explain or justify using Coulombic attraction. Thanks, everybody. Have a nice day.